I would like to invite Dr. MARYAM SHOJAEL on the dais. Ma'am, please. Welcome, ma'am. I'll take this up.
It's not updated. It's around
Okay.
6-7 years old.
But that has been shared actually.
You could have taken from it. It's okay. I mean, okay, I just announced this is 7 years old. So you can continue.
Ma'am has overall like more than 10 patents national at international level.
Maybe I can.
Okay. I'll give the mic to ma'am only. She can more better elaborate herself. Sorry, ma'am.
So, yes, and then see that how we can convert it to publications, patents, startups, translational research. So everything that you can think of could be the outcome of our brain and thinking. So therefore, really what matters is that to have confidence and then generate all these publications, everything are generated and have come working with people like you, like the students like you and the colleagues like the faculty here. So the culture of teamwork and culture of being involved in everything, so it's very important. So we also work as a student. We have to play two roles. The request is because my slides are too many, and the reason is because I want to keep the continuity. However, I will try to keep the time. In case, for example, I'm crossing the time, you please give me just 5 minutes advance note, so then I will try to wrap it up. Okay? Yeah, actually morning we checked, everything worked. Hopefully it will work now also. Only laser pointer and I have to see it. I have to sit there?
Just for 5 minutes.
Oh, for 5 minutes. Sure. I'll sit. Don't worry. I will not take your place. Just to connect.
Before starting the session, I request Bhandari ma'am to please come on the dais and felicitate Dr. MARYAM ma'am with a floral bouquet. Thank you, ma'am. Now we'll all start with the must-awaited session. I'll hand over the session to MARYAM ma'am.
Okay, so then let's start, and feel free to ask questions also, so it's okay. So though we can have question answer at the end, but I will be happy even if you just raise your hand and ask a question. So as I told you, I will make it very flexible with respect to the slides. And then I thought it would be better to keep the entire information about the conference on the right side rather than putting only the conference logo. Okay. So today we want to talk about the integrated circuit and electronic systems for AGRI sensing. So this is part of almost like I started working in this domain from 2012. So it's around 10 years. And during these 10 years, I learned that how we need to really work in different domains, not by ourselves, but as a part of a team, and then how to connect and integrate. Things which may look very simple and different from the activities, students' activities that today morning we visited, but could be of interest, and it's important also for the country. And I want to connect it also with a new initiative from the government of India and the semiconductor mission, and therefore how simple things can become an opportunity. So I have two parts in this talk, and then first part is just to take you through a journey of one PhD project. We were discussing, in fact, about PhD research. So with PhD, we learn how to solve a problem which is not solved before by anybody else. So that is the definition of PhD. Now to learn that, we have to face challenges, but when we solve only this one single problem, you get that capability to solve many problems. Of course, it's not necessarily to do PhD to get that strength. You can even, naturally by working on challenging problems, earn that strength. And that becomes after some time a habit that you can even live it. So continuously you become a problem solver. And that's the way that we want the engineering to go. Problem solving and then implementing the solution in real world. So first thing is, and I try to keep it very simple, therefore my examples are actually simple. So let's talk about a simple ASIC, which is application-specific integrated circuits. We want to design an IC. We want to send it for fabrication. We want to fabricate it in a foundry. We want to get it back, get it tested, then make a prototype system, and then characterize it. So the whole journey, therefore the PhD student needs to get through the entire journey. And the advisor has to be with him or her, otherwise they don't know how to proceed. So therefore it's always a kind of learning for both sides. So we always learn more and more as we work more and more. Problem is the soil moisture measurement. Soil moisture measurement is not a new problem. And today when we talk, even 10 years ago, when, in fact, this project also was suggested to me if I can work on it in collaboration, I thought there is no component of research here, but it will be good to develop a product. At that time, the motivation was to make it cost-effective. So still, I thought, okay, this is a project within a year or two, we can finish it, and it's for 10 years now we are working, and 3 projects proposals, and still is continuing. And the reason is because there are interesting problems that don't come to the notice. For example, even today, you don't have worldwide a soil moisture sensor, which is reliable, can work on its own in the field, on its own, without anybody to check it every week or every month. It works under different temperature range values. It doesn't mix up the temperature variation with the soil moisture variation. It is robust to all kind of field problems, starting from insects, animals, theft, humidity, rainfall, and snowfall, if it is in other places, say at north of India, or even anywhere else in the world. And it is still economical, affordable for agriculture sector. Agriculture is a sector that you cannot directly reach to the customer. It's very difficult. Agriculture is a sector you have to indirectly reach the customer. You cannot sell anything to farmers. Farmers cannot pay for any product. Therefore, the business model even is different. Until today, this problem still is not solved, because this problem needs scientific contribution, business contribution, product contribution, product manufacturing contribution, distribution, and the kind of the model where the end customer doesn't pay for the product. So how to make it sustainable. So see, it's a very complex problem. And I didn't know it's so complex, which looks simple. So therefore, what is the soil moisture measurement? You can tackle it from different angles. It's a problem related to agriculture. We put civil engineering aside we put finding water in Mars, on Mars aside, because these are also different applications where there are different levels of the budget available for these applications. So looking at the farming only and only agriculture, the question is that how we can measure the soil moisture. There are different ways, and as electronics engineer, so therefore we look at electronics methods. So one way is to measure the dielectric constants. There are products which already measure the dielectric constant, so there is nothing new here. But how to make a product which can become affordable? Therefore, it has to be a very simple product. Therefore, we don't look at complexity. But at the same time, we want to see how it can be manufactured in India itself. Therefore, it should be a design which is compatible, say, for example, with the SCL technology. So to make it compatible with that, therefore, we go with a foundry which has the technology similar to SCL Chandigarh, so that fabrication also can be within India. If fabrication is within India, there will be a lot of cost saving. And this is in the direction of semiconductor mission. So the simplest, one of the simplest structures that you can think of measuring the dielectric constant of any media is to have two probes, insert it in the media and measure. What we are measuring, actually we are measuring something like a fringe field capacitance, where the field lines start from one plate and end in the other plate. Say, for example, this is one plate and this is the other plate. Fringe field starts from here, ends here. Now, depending what is surrounding or covering this probe, you will get some number. And what is this number? Now, that value of the effective capacitance, you see, which is in the form of the fringe field. So it's not a plate capacitance, and therefore the direct field doesn't exist much. The main field is fringe field. So therefore, the basic concept is a simple physics concept. So now, by changing the moisture content, naturally dielectric constant value changes. So therefore, we think that this would be reasonable to use it as a method for measuring the moisture content, and this seems that to be reasonably economical. So why not to just go ahead with that? So the first point comes, and the first scientific challenge comes, the dielectric constant of the water itself changes with frequency. Therefore, if we want to use a method, we need to know what is the frequency at which you want to measure the dielectric constant. So we go a little into the physics. Therefore, the first thing we need to know is the model of the media, the model of the concepts of the physics that we deal with, so that we don't make a wrong choice. See, if you choose a wrong choice of frequency, whatever you make will not give you the right value, because it is not the right frequency. And what is the meaning of right frequency? There is in any media, and eventually there is a lot of kind of resonance available in molecules, between molecules, atoms, and electrons. So these are all inherent to the material. So this results in different kind of characteristics of the dielectric constant for both real and imaginary part of it, and therefore we will not get a straight line. For example, if we look at the real part of the dielectric constant, so it's not flat for all frequencies, and imaginary part also is not flat. Imaginary part of dielectric constant is a representative of actual loss of energy, and the real part is what actually we use when we want to calculate a capacitor. So therefore, assuming material is ideal, so this imaginary part will not exist, and there is only a real part. But actually, dielectric constant is a complex number. So now we want actually to measure this complex number. Answer is no, actually. We don't want to measure a complex number. All we want to measure is to measure this epsilon prime, which is changing with frequency. So what is the right choice of frequency? Look at this range of frequency, which is almost giving a fixed range, fixed value for epsilon prime and epsilon double prime. And this eventually behavior, which is called this entire, of course, frequency behavior due to electronic, atomic, and dipolar effects is called Maxwell-Wagner polarization. And this creates eventually variation of dielectric constant because, by different values of the moisture content. Therefore, if we want to be on the safe side, we need to operate only at this range of frequency. This range of frequency covers almost like 100 megahertz to 1 gigahertz. Therefore, the first information we get, we should not be too far below 100 megahertz, and we should not be too above 1 gigahertz. So see, this first point itself, we may not even know it. In fact, honestly, I was not aware of this behavior. And then we learned, and therefore it allowed us to go with the right choice of frequency. Now, if we are operating at those frequencies, then now the story changes compared to the case we are operating at kilohertz frequency. The second thing is to start simulating that device that we want to fabricate, understand what are the parameters we have. What is the approximate even analytical model if it exists? That helps in the design. So therefore, another part of the research, which is still connected to the real problem, is to have an approximate model if fringe field is the actual determining the value of capacitor. So it's an approximate model. Choose a proper simulator, for example, HFSS simulator, because now we are talking about frequencies above 100 megahertz. And finally, have some estimate of the right values. So how to choose the length of the probe, how to choose this gap between the probes, how to choose the width of the probes. There are pros and cons. For example, if you reduce the gap too much, then you don't get enough information about the material between the two probes. And therefore, electric field lines will cover a very small kind of number of molecules when they start from one plate and then on the other. And therefore, you will not get the proper effective average dielectric constant. Because soil is not a uniform homogeneous material. It's actually a mixer and complex. If you collect a sample from a land in Pune, agricultural land, and if we collect the agricultural land in Nagpur, and then we go, for example, to Karnataka, characteristics change, even for a given soil moisture content. So therefore, it's completely even geographical location dependent. So therefore, we need to keep enough volume to be covered here. So this is the parameter. If we make this probe too tall, implementation will be a problem, because you need to dig, you need to insert, and you need to remove this probe. So it becomes fragile. If you make it too narrow also, it becomes fragile. So, and if you make it too wide, it becomes difficult to insert. You need to dig, you have to proper auger, so protocol changes. And also it has impact on the structure of the soil. Ideally, we need a non-invasive method, but I'm talking, we have non-invasive as well, but just I'm talking about the invasive method. So this is the second part of this journey. So till now is everything about idea. And what we want finally to do is to make a chip which does everything, the processing, and then transfer output of the chip to the outside wall through these SMA connectors. So now here, after several simulations, optimization that takes its own time, and I don't want to get into that, just I want to show you some of the differences also between real and actual model. Suppose you want to put a relatively simple model of a capacitor at high frequency. One model is to have parasitic series resistance, parasitic series inductance, and the capacitor. Therefore, naturally, you will have a resonance frequency for the sensor. So therefore, we need to know where is the resonance frequency. Means from where really vicinity of which frequency this L will come to the picture, because then the behavior will not be capacitive anymore. So therefore, we need to know what are the non-idealities. We need to know them, otherwise again measurement goes wrong. In fact, there are many soil moisture sensors in the market which operate at kilohertz frequency. And I'm always wondering that, how they operate. on what basis they calculate or they measure at kilohertz frequency. And actually, we purchased even the cheapest soil moisture, which is, I think at that time was 150 rupees. It worked only for 1 day. So we tried many products at the beginning, but nothing worked except around, I think, a 3 lakhs product, which is not feasible. We only purchased it to use it for the referencing, but it's not feasible as a product to give to the farmer. So it's out of question even. So for example, you will use a standard material. For example, this is white clay. So this is the way actually that probe is used. So you insert it within the material and then do characterization. We start with the standard materials because the behavior of the dielectric constant is very well available in literature, and they are used actually as reference material. So therefore, to do that, you need something like a vector network analyzer because it has to work at high frequency. It has to give you all parasitics elements. So you use a vector network analyzer. So it's not really measuring capacitance directly. You need to really use a sophisticated instrument like this instrument, which is a portable vector network analyzer. Even for characterization, we need to have it. So this is, for example, one model, N9925A. So now here you see 3 material. First, of course, is air. Everything starts with air. And you see the black is measured and the red is the fitted, eventually extracted these 3 parameters and the model of that parameter. Naturally, measurement will show some fluctuations with frequency. Even if you change it, I mean, repeat the measurement, you may get a little different. But if you look at the an average or envelope of this plot, the red color still is showing the behavior of this model as compared to reality relatively well, except for glass beads, which is still okay because this is at the resonance frequency and we want to operate it well below the resonance frequency. Therefore, that means that we have to choose frequencies around, say, 100 to 200 megahertz so that we would be able to get it well for all kind of materials, at least standard materials. So this is the 3rd step. 4th step. We don't want to use VNA, such as expensive instrument again. What we want to do is that we want to use a simple ASIC, which is designed by us, and then make a chip, and that chip will do the measurements. Therefore, here is the question. How do we measure a capacitance? There are different ways to measure a capacitance. Let's convert the problem into how to measure a resistance. Suppose you have a simple resistor, and then suppose you pass a current through that resistor, and the value of that resistor changes. It's a sensor. So therefore, the voltage across resistor changes. That's the simplest idea will come to the mind. And operating at DC. Operating at DC. There is a step here. So operating at DC. Actually, you don't need a step here anyway. So operating at DC. Here we don't want to operate at DC. And here we don't have a resistor, but we have a capacitor. So what we do is, we use still same idea. See, simplicity is the best way to do innovative things. And unless we don't think simple, we cannot simplify problems. If we don't simplify problems, we cannot give new ideas. Because that is the way our brain functions. So therefore, the way we do is that we just go with the same idea. There is a current source flowing through a resistor. But what is that resistor? We don't have a capacitor. How we can convert a capacitor to resistor? So this is where we go back to another thing that we have learned, and then we use it, switched capacitors. If we switch a capacitor with some frequency, we would be able to emulate a resistor. Now, because the capacitor is switching, see, you know, this is something new that more often doesn't come to the mind. Capacitor is switching with that frequency, above 100 megahertz. Therefore, the capacitor CS, which is actually due to the sensor, is dealing with that frequency. It's getting charge and discharge continuously with that frequency using these two switches through this current source and discharge to the ground. So the capacitor will see that frequency. However, we put a large capacitor, say 1 microfarad, at the output of this circuit, and we filter. So therefore, this kind of sawtooth waveform, on average, will give us the voltage. So we get the average, we get almost like a DC value at the output. If we use a very high value of CF, we will get less ripple, just the way you design regulators, voltage regulators. So therefore, this is actually the simple method of I to V converter using a resistor. Therefore, it's a resistor to V converter, voltage converter. We emulate resistor with a switch cap. Therefore, it becomes a C to V converter. And that is all we want. Therefore, we still measure a DC, but we operate it at very high frequency. Therefore, we don't need VNA because we don't measure directly. All we do is that we measure indirectly, and we measure only the DC voltage. Now, if you have that, everything is simplified in this relation. 1 upon F in CS is equivalent resistance of a switched capacitor CS at frequency F in. I in is the DC current that we fed into that, and we can program it depending on the range of CS and frequency. One more thing here you see is RS. Why now we have to be worried a parallel shunt resistor? Most of the soil content also is getting mixed with ions. Where do they come from? They come from irrigation water, they come from fertilizers. So therefore, naturally, because of the existence of these ions, we don't have a simple capacitor. We actually have an RC filter, RC element. So this is the extremely important part which comes to the picture. So we cannot just have, therefore we have to make sure this RS is not creating error. Therefore we need to see what is the minimum value of RS, which is not giving us error, and whether that minimum value is compatible with the practical soil samples that we have. Though this technique is not only for soil moisture measurement, it's for dielectric permittivity measurement. But I'm giving an application for that as an example. Next thing in ASIC design is when you have a simple circuit which is on the left and what you have on the ASIC are not exactly same. When you want to convert a simple circuit to a working circuit, it takes more effort to convert it to a working circuit. Give you an example. You want to give this clock to these switches. These switches are on the chip. These switches should not have a very high resistance. They have to be low resistance. Otherwise, it takes time to charge and discharge this capacitor CS. So therefore, we will go with a very large switch. And you may know, if there is a switch which is large, when it is on, it will have a huge charge stored in the channel of switch because it's a MOSFET switch. Therefore, when you turn it off, this charge has to be discharged. And discharge of this charge will go to the capacitors which are at the both sides. And this will create error. To avoid that error, these dummy switches, which are operating with the opposite phase, have to be put both sides of the switch to absorb the charge and absorb also the clock feed-through effect. So therefore, you need to compensate for that. So dummy switches come to the picture, which are not here. Here you see just ideal switch. Next thing is that because these switches are large, you need to put a tapered buffer to bring these switches, output of this clock to the switches. Clock should come directly to switches through buffers. So therefore, because these switches are large, so something has to drive them. Then you need to design these buffers, tapered buffer properly. Now to drive them, we need actually two non-overlapping phases and invert of them. Therefore, we need complementary clock generator. So we have to put it. Here we just wrote phi 1, phi 2, and that's it. But now we have phi 1 bar and phi 2 bar. So we have 4 clock phases. So therefore, this circuit in the green background will get added. Then we have to generate non-overlapping clock phases. So this circuit also will be added. Then we are transferring the clock from outside because to have freedom. Later, in the current tape-out, we have moved the clock generator also on the chip. So for the first tape-out, we kept it outside. Then we should have tapered buffer, this tapered buffer at the input to make the waveform clean, because this clock is working at those frequencies. I don't know if you have had the experience of giving clock to an IC on a board at frequencies above 100 megahertz. Because of sharp edges and RLC effect of pins, you will get ringing. And therefore, clock edges will ring. But you cannot give a ringing clock to this circuit. So the whole circuit will get affected. So therefore, we need to put a tapered buffer properly to make the rises edge again sharp on the chip. Now you have a reasonable kind of design by putting pad frame around that and then send it for fabrication. So this is the next step. So just to repeat same thing, but just for some information, we use 180 nanometer mixed mode technology, CMOS technology, to make it compatible with SCL Chandigarh technology. We use low VT transistors, low threshold voltage transistors for switches, so that the size of these switches becomes reasonable, because gate overdrive can become maximum if VT is the minimum. And dummy switches are added, and non-overlapping clock generator were designed to work across all process corners. What does that mean? Because for any technology, there are variabilities. Therefore, to manage those variabilities, we need to make sure for all range of VT values, this non-overlapping clock phase generator works correctly. So now till this point, and this is by one PhD student, but system level work, there are MTech students who help. So now you see the size. This is actually the 0.02 millimeter. So it is inverted because I moved the figure this side to make it better, but actually I forgot to. This is 0.02 millimeter, 0.3 millimeter. So this is like 300 micrometer, and this is 20 micrometer. So this is the size of the entire chip. But you may say that if this is the size, why your chip is so big? The reason is when we want to send a chip for fabrication, the service provider will give us a minimum area of silicon. Therefore, we cannot afford to have any size that we want. Therefore, we need to put several projects together and then submit it for fabrication. So almost like 3-4 PhD projects are combined in this chip. And then everybody will take a few samples when it comes, which is on the right side here. And then they start testing. This is the test board. This is just a pictorial view of the same layout after fabrication. This is die micrograph. We call it ASIC AGRI 10.1, and similarly a test board for that. So test board has clock as an input. Test board has the ASIC. Test board has some power management, arrangement, and arrangement for giving the input current. So this is the test board. So this is now where to test it. And to test it, we start with a programmable standard digicap IC. So we don't jump to testing with real material, because it gives us flexibility to see over the entire range. You know, if you have worked with any digicap, this is an example IC of digital capacitors. What it means that eventually you give the code, you get a cap. It's like a digital to capacitor converter. So you give a code. For every code, you get one value of capacitor that you can use for any application. It's like a DAC, digital to analog converter, but instead of the signal, you get a capacitor. So therefore, it has different states. For example, here is almost like 32 states, equivalent with 5 bits. And you get values of capacitor from, say, around 2 picofarad all the way to around 15 picofarad. So this would be eventually the range. Now, if we have this range, and we chose that because it is reasonably close to what we have to, even it goes beyond that. So We need also to look at the actual, nonlinearity of this DAC. This is a kind of measurement of nonlinearity. For every step, how much variability we see in the step. The steps are in the range of hundreds of femtofarad. So this is what actually measured using ASIC, and this is what measured using VNA. Measurement through VNA, which is as per, data given in data sheet, compatible with that as well, is for reference. And this is actually what is measured using ASIC. And you see that really a very nice compatibility. So therefore, you get the confidence. Now, if it works using passive elements, then you can move to the actual elements. Actual elements here are actually samples. For example, kaolin clay. Kaolin clay is the actual sample. So now the same board with ASIC is used for kaolin clay. And this is the test board. So one thing interesting here, you see the volumetric moisture content to measure and frequency is 100 megahertz, minimum we could keep. This is the difference you see, like around 0.49, 0.09, and 1.87. So how much error we can afford? When you do a measurement, if you repeat it, you will not get same values that you have measured. You may try it. It's unless if you limit the accuracy to say integer numbers or one digit of their point. But in many cases, you don't get same numbers because the conditions of measurements change. Characteristics change with the temperature, humidity, even with time. The question here is that how much error we can have. We don't know. Who can tell us how much error we can have? The people who are actually agriculture scientists. Therefore, we have to go back to them and say that, see, look, how much error we can afford. They say that if you want to look at the agriculture and farming, plus minus 3 is more than enough. So therefore, we use this plus minus 3 as a benchmark. And this didn't come from one person. It came from many people. So therefore, it will tell us that only first one doesn't seem to be right. But look at the first one. First one is actually the moisture content is so low, it's almost dry. So being dry, there is not much difference. Of course, if you convert it to volumetric, 0.01 becomes 0.5. Gravimetric means mass, volumetric means volume. Volume of water or mass of water. So volumetric is a standard one. So 0.5% is very low. Like that means 0.5% is the volume of water divided by volume of dry soil. That much water you have in the soil. So it's dry almost. So therefore, really, this much error is not a big deal, though the window is actually plus minus 3 in percent. So this is also in percent. So this, therefore, we are really well below this window. That means already it's good enough. Even we didn't need to do more. So this is the whole setup. Today we were discussing, definition of PhD. So we were just joking that it's a doctor of philosophy. I said that P is more for patients. Anybody now wants to do anything, not necessarily PhD, any kind of research which can result in something which close to a product or can be converted, need to be patient and see the problems and challenges and peacefully try to solve them without being in a hurry. So therefore, we were joking that, okay, really PhD means that really doctor of patient. B, get the doctorate in how much you can be patient. So P is for patience rather than philosophy. So this is one example of patience. Even to make a setup, which that you know your setup itself is right. It takes days and weeks. It's not a 1 day and 1 hour job. So effectively, it's the whole journey of a PhD over the span of 4 years. So setup eventually is everything is set. We need to generate a signal. We need to read the value of current. You know, we have extra pins to read. We need to read the currents because we need to make sure ASIC is not malfunctioning sometimes. Because it's an ASIC, it's not a commercial IC. We get it fabricated by a commercial foundry, but they give us around, say, 20 chips, packaged chips. So they have not gone through the quality check, so we have to be very careful. But here now, just to show you how frequency is important, on purpose we did this measurement. Looking at these are the measurements which are actually performed and then back calculated to the capacitance. See, one is at 95 megahertz and one is at 100 megahertz. As you notice, at low values of moisture, because value of water is low, 95 megahertz and 100 megahertz don't make a big difference. As you increase the amount of water, and this say, for example, between 20, 30 to 40%, actually is very important. Because that is where you need to decide you should not irrigate. That is where the farmers have to decide not to irrigate. Because soil is already getting saturated. Therefore, and when to irrigate? For example, in this range, 30% should it be irrigated or not? So even with drip irrigation. So therefore, this variability creates a problem. It's just a dependency on the frequency. And that's why choice of frequency matters. And we need to stabilize the frequency of measurement. This experiment was actually performed on the red soil with the texture of loamy soil. So there are standard ways and semi-standard to extract the soil texture. We do that. We have learned a lot of things about soil over these last 10 years. And that's good to learn things beyond our domain so that we can apply what we know in our domain to other domain. Because those who are in the other domain don't know anything about this. When we talk with agriculture scientists, they say, you take care of this. We don't know anything about it. It's all your responsibility. We just can talk about soil and plants. So that's why we need to know now, therefore, their side so that we can communicate with them. Fine. Okay, so fine. So therefore, I go only with part one. Okay. Yeah, so this is just I kept here to explain. And the overall, the measurement error that overall exists here right now is plus minus 2%. See, if you have error of plus minus 2.1% plus other sources of error, can make it beyond the plus minus 3%. That's why we need to stabilize the frequency. But this is not only from product, we were looking at the affordable product, but also from research point of view, it's really attractive. For example, with respect to consumed silicon area is the best at the time of report. We have published it in Feb 2023. I think I included the paper at the beginning. No, I didn't. It's okay. Sorry? Fifth? Yes, thank you. No, this is actually, no. Okay, this is the ABSCON conference paper, which was only with respect to the model and the characterization of the standard material and comparing them with each other and how to eventually set up this in the lab. We have a journal paper. Okay, so no problem. So anyway, in that journal paper is actually IEEE Sensors Journal, February 2023. So see, this area of silicon matters because it determines the cost. Power consumption is reasonable, depends on the frequency, and therefore we have a range because we were changing the frequency. And also depends on the value of the DC current we consume. That also is programmable for us. So we can effectively operate it, of course, from 25 megahertz to 250 megahertz within this range, though we use the fixed range of fixed value of 100 megahertz. And this RS that I told you is very important. Down to 5 kilo ohm, for that probe that we had designed, it doesn't have any effect. That means that for most of type of the soils, with any reasonable amount of fertilizer, it can work. 5 kilo ohm actually is very low. In practice, you get more than that. Other methods are not really covering this part, and therefore, all of them are sensitive to this value of parasitic R. And another thing is the range of capacitor. For us, is around 10 femtofarad to 24 picofarad with 4.5 picofarad offset value. because there is pin capacitance, parasitic capacitors, pad capacitance, I/O pad on the chip. So we need to deduct it. So that's why this 4.5 comes as a DC value. Or if you don't have anything, you have only air, you get 4.5 picofarad. Let's put it that way. We don't need any reference capacitor also. It doesn't need any referencing. So that's another advantage. And resolution is pretty good as compared to, or at least comparable with other reported works. Under this kind of wide range and insensitive to the shunt resistor of above 5 kilo. So this became a kind of looking at the simplicity, looking at the non-idealities, looking at the right choices, but it became a research problem. Therefore, if you want to just make a simple solution for a large-scale problem, extended everywhere, so effectively it brings us to new problems, and new problems result in new innovation. So then I stop here, and maybe I can just go to the, sorry, I had actually many things. But these are some of the collaborators, PhD scholars for all the kind of projects in agriculture domain we do. Electrochemistry, screen printing, paper sensors. So a lot of them are going on. So therefore we have a group of people who have expertise at different domains effectively. And all are supported by METI, DST, and 3 labs in the department. VLSI lab for chip design, embedded system lab, and integrated system lab for chip testing, and the entire department. And we use Europractice service for foundry. However, we also fabricate in SCL Chandigarh. And I would mention that process is very stable. Chips work in the first run. So therefore, really, there is a possibility to do mass production of the chips fabricated within India. So it's an end-to-end kind of solution. Nothing can go, because packaging also can be done within India. Okay, thank you. Thank you for that. Sure. Should I disconnect?
Thank you, ma'am, for sharing your research on agricultural domain using sensor technology. Okay, anyone is having question? Sir is having question.
Hello.
Madam, I am
Yes.
from IEEE, and we are working on this affordable agriculture in the Pune section.
Very nice.
So this was very interesting topic for me and those who are involved, those who are listening online also. My point is, from the capacitance point of view, you are trying to excited by that 100 megahertz to 200 megahertz switch. And it seems from that slide that there is a small time difference between the two switches. One is
They are
discharge.
non-overlapping.
Yeah,
They are
yeah.
non-overlapping clock
Yeah,
phases.
yeah, yeah.
Because when we charge the capacitor,
Yeah.
we should not allow the discharge switch to turn on.
Correct.
Otherwise, there will be a short.
Yeah, there.
So therefore, charge-discharge will. This is
Yeah.
eventually the requirement which comes from switch capacitor circuits.
Switch
There also everything operates with non-overlapping clocks.
And what could be the expected capacitance value in your circuit or in your?
Okay, so it depends on the size of the probe.
Okay.
So, like, of course, shapes of the probes are different. We chose, what I showed, one of the simplest ones that we wanted to really be the lowest price. So this has 3-4 parameters. One is the length of the probe, length of the two probes. One is the width of the two probes. One is even in the thickness of the PCB. Because this also we use PCB material, peace of mind. We have other versions when we use different material and then we use a screw to connect it to the PCB. We tried all possible combinations. But this one is the simplest one because in one shot you can get the whole PCB and put the ASIC on it. So therefore, length of these probes, width, thickness of the PCB, and the gap between the two probes are optimization parameters. We have a range for them because of the field constraints, and within this range, then we actually use the simulation to get what is the range of capacitor that we will have, depending on the variation of the dielectric constant with the moisture.
I have got one practical consideration, which I probably might have missed, that you are trying to measure it in situ.
Yes, it is in situ.
So when it is in situ, how do you apply such a high frequency, or the whole circuit sits on the capacitor?
Yes, that's a good question. Right now, we have applied it through an external clock generator.
Okay.
We have the second version of this chip, which is now in the foundry. It's almost like at the packaging step. We have a PLL on the chip, which synthesizes the clock. Correct. And the clock internally is produced and goes to, so therefore, from external user, only a DC voltage is seen. There is nothing else.
Thank you. Actually, I was wondering how you
yes,
can do
yes,
it
that's
inside.
the right question. Yeah, thank you. Yes.
But then you transmit it to the user because
yes,
I'm
this is a DC voltage. Yes, so this is a output is a DC voltage.
Yeah.
Therefore, you can easily transfer it even on a wire, because you don't have any problem with DC transfer.
But in the field, actual farm, this may not be a good
No,
thing.
actually, we have a pole. We have a pole, and then we have a wire.
Okay.
And this wire carries only this DC signal, and which is supply. And then takes the DC signal, which is output of the chip. That wire goes with this probe, and probe goes to the ground.
But this is simply to measure the soil moisture.
This is right now, yes, for soil moisture. Application was defined that way for the project, yes.
Yeah, that means first I do my survey of the soil moisture, even with the wire connected to the probe.
Yes,
doesn't
yes,
matter.
yes. It doesn't matter. Right now it doesn't matter because this application is for farming, not for characterization of the farm.
Correct.
So therefore, when we talk to landowners as well as farmers and scientists, three groups we eventually talk to, and they have different levels and different types of knowledge about this area. What they say is that we don't need really to measure every point.
Yeah, true.
Because there is enough variability. What we need is to measure, say for example, let's assume area of this salon is a farm. So say you take 4 corners and take 1 point at the middle. So, and suppose you have drip irrigation. Drip irrigation is something I personally am very interested. So that's why I focus is on drip. Some farmers use flood irrigation. Problem with flood is non-uniformity and too much water. So drip works very well. Like most of the scientists recommend drip. Now in the drip irrigation, already this is going on. So therefore, all you need is to put some sampling points. And these sampling points, for this area, you don't need more than 5 sensors. Therefore, 5 sensors will give you a very good idea about what is the profile of the irrigation. You see the variability also. There are 4 corners, 1 or 2 at the middle. That is enough. Some farmers actually divide this land because of the uncertainty in the crops. They divide the land into 2-3 plots. And each plot, they actually have different types of crop. So they say that for 2 sensors per plot will be fine for every, for example, type of crop. This is for small-scale farmers. One thing I tell you is small-scale farmers have the area of a couple of acres land. They are not really big. Therefore, it works very well for them. But the number of farmers who have a small-scale farm also is very high. And if we assume that all can reach to a much better productivity of the crop, there is a huge boom in the productivity of the crops that they have. And that, the only point is, they cannot pay for these sensors. Therefore, even though they are cheap, still they are expensive for farmers. So we have to find a solution. And the price that we are talking about is either 4-digit in rupees or 5-digit. 3-digit in rupees is very difficult. And it's not manageable. They come from China, but we try them, they don't work. Reliability is very important. Put it in the field. Who has the budget to send technicians to the field every week to check all these sensors? You need an army for that. So that also is not feasible. So there is no manpower here as well.
But I can offer it as a service.
Yes,
Yeah.
that's why NGOs are here. NGOs actually play a very important role. Some of our connections goes through NGOs to the farmers. NGOs, but still NGOs are not good enough to provide all these services. Because NGOs also, you know, I mean, they have their own defined services. So if you say that, okay, we will give you this service, every week you check these sensors, see what are the problems, report it. We have found it is not very safe. They do it for 1 week, 2 weeks, but this has to continue for the entire season. Practically, there are 2 seasons per year for 1 crop per farmer. So it needs many people, many people.
Thank you.
Yeah.
I have one. My name is Sheetal. It was wonderful talk, madam. The question which raised in professor's mind, even raised in me, my mind, that why to have that large buffer range and have a V in or V source outside? So what was that? What made you to keep V source outside initially, and now you are pushing it the next version inside?
Yes, that is another question which goes back to the practicality. So we have 2 constraints, and I think all of us have that constraints. One is the budget, money, and one is time. So in a research project, anyway, we have to keep the timelines. So money is a problem because, do you think how much is the cost of this IC for us? How much it took, amount of money we paid for this IC? 20 chips, 20, just 20 ICs. How much it takes for you to take 20 ICs from market? Say 20 op-amps. Any IC, have you ever purchased, ordered any IC from, say, DigiKey? Any IC? You have never ordered?
Somewhere around 100 if it's simple op-amp, not
100
more than
rupees.
Yeah, for simple 741 kind of thing.
100 rupees.
Which are get mass produced, but I'm sure that this must have cost.
That's
very
exactly
high.
the point. You are absolutely right. That's why I emphasize on 20. This is 20 ICs, not 1 million. Therefore, 100 rupees is not 100 rupees. For 20 ICs, we pay 4 lakhs. Each IC costs us 50,000 rupees. And you cannot repeat it. Even if I am ready to pay another 4 lakhs, I have to wait for the next tape out. Because foundries give these services to institutes on a specific time of the year and date of the year to make it compatible with their commercial services to industry. So therefore, if I miss, for example, April tape out, I have to wait till September tape out. So therefore, time and money. Now the question was, why clock sources output? To make a synthesizer, you need a PLL. PLL was another project, right? You eventually end up doing 2 ASICs. Therefore, what we do is that we do ASIC by ASIC, and that is what industry does. The ICs you get right now and use it in the systems you want, they are designed 20 years ago. They have 3-4 generations within industry, checked, debugged, tested, again next, till it has become complete. Industry sees what comes to the market in next 10 years from ICs. And they are designing, debugging, and going with generations of those IC within the company now. They always 10 years ahead. They know what will come at next 10 years in the market. So therefore, we should also follow the same, because that is the way they are able to manage it. Industry also has the same problem. For industry, it even is more, because for us it's 4 lakhs, for industry it will be 40 lakhs. It could be 4 crores, because our prices are discount prices, academic prices. Now for them, therefore what they do is that they do exactly this. Divide the task across several generations of this ASIC till the last one is actual. And therefore we kept the signal outside, because our project is not synthesizer design, it's the sensor design. Let's finish the ASIC. If ASIC works well, sensor is giving proper characteristics. Now the second design is the same chip plus a PLL sitting on the chip. That was the reason.
Yeah, and one more is like RS, how you model that resistance, parallel resistance, because I feel that with the different soils, types of different soils, this RS would be different, because ions in that soil would be different. And how then we model it and ensure that our product works fine in all sorts of soils?
See, actually this RS even is not constant, it changes. So we don't need to really look at the modeling of the R, because all we need to know is how much is the range of the R. R could be infinity, which is the ideal case. And R has an R mean, minimum R. For us, the minimum R that we can manage was a problem. So we just did the test and see that if we want to remain within plus minus 10%, 3%, how much is the passive R that we can make parallel with the C? We did it actually. So it came out with 5 kilo ohm, we can manage. Below 5 kilo ohm, we will cross the error. That's why we reported 5 kilo ohm. Now, any soil, and this depends on the size of the probe as well. So for the given probe, for any soil, which will give 5 kilo ohm, series, parallel resistance, eventually it's the conductivity of the soil. This design can take care. If it is more than that, error will increase. Then we have to design a better sensor. For example, in a parallel PhD project, we work on the RC sensors, which are independent of R, for lower values of R. So therefore, it became a new problem and a new research problem. So therefore, it went to another student.
Maybe
this way.
Is last one. This is about 3% is allowed range of accuracy. And your result shows that we have reached somewhere at 0.2 or something like that. So is it not overfitting? If we still make it reach to 3%, will there be any price where we can save on and make it more, or something where we can save, maybe design efforts or price, and we can still work with 3% in the market?
Yeah, that's also a very good question, but only tell you that these numbers we got in the lab. As soon as we went to the field, we reached to 4%. With the same thing, that's the difference between lab, because in lab you have a soil which is under all natural conditions and you cannot emulate them in the lab, even though we take sample from the same field. So therefore, in fact, that 4% we had to, in fact, within our technical committee of MEITI, because our project had 2 committees. One was technical committee, one is finance committee, and 2 reviews of technical. And that was also a mixture of scientists. So they told us how you can take care of this 4%, because it's 3%. Now we had to see how really we can work on this 1% to manage it, which is still, for some fields, not for all. So therefore, actually, when in lab, you get 0.2 and 0.5, that is because in the field you want to get 3 at least. It gets worse, therefore we need to design for better than that. Yeah.
Thank you very much. I'll keep few to myself so that I read your papers. Thank you very much.
Thank you. Thank you. Thanks for questions.
Hello, ma'am.
Yes.
I am second year student from ENTC department. My question might be very immature, but I have to ask.
No problem. Good.
Okay. My question is, capacitors with dielectric allow a very small leakage current, very negligible leakage current through them. But now with moist and conducting dielectric in between, current becomes significant and have effect on the calculation of capacitance.
Thank you. This is actually covered in the shunt capacitor. See, RS actually covers any parasitic conductivity which comes for that capacitor. Therefore, it covers leakage as well. The leakage you are talking about is actually coming because of ions in the soil. It's a leakage, right? Because this capacitor is not a real capacitor. It's like a capacitor, but not below 5 kilo. Otherwise, our error will cross 3%, even in the lab.
Thank you, ma'am.
Yeah. No, good. You ask questions. Asking is absolutely. Sometimes I ask questions from my students to learn from. That is the best way. We challenge each other.
You can have a seat, ma'am. Once again, thank you very much, ma'am. It's
Hello.
indeed... Okay.
Just
One more question.
Yeah. I work in embedded system. I guide projects on precision agriculture, so on this. So this is very much related to this. My question is how the looseness...
Distract the structure of the soil, which is okay. And then they start eventually seeding, and then it goes with the next stages. So if you put probes at this stage in the soil is not very rigid, it's soft, and then there are voids in the soil. Over one season, gradually this soil becomes very rigid and hard. In fact, if after plowing, sensors have to be inserted, simple probe insertion, or even if you try just to put a stick inside the soil, you see that it is much easier if you do it in end of the season. Because during the entire season, nobody touches this soil effectively. So gradually it becomes hard. And sometimes if you, like for us, we had kept sensors in some place next to the field so that it will not even explode. And then in one case, we have 3 years deployment. And then after 3 years, it was so hard that when people, one of my students also had gone there, he actually broke the sensor. The sensor, which was at PCB, even though they tried to dig. So now your point is correct, so it changes. Therefore, naturally, when this void area and compactness changes, soil density changes. And because of the variation in the soil density, conversion from gravimetric to volumetric changes, because you need to multiply by the density. Now, because of that, there is an error. And this error, in fact, was one of our discussion with MATI Technical Committee. That the scientists were telling us that you actually get how much the soil density is changing. It turned out, actually, the variation of the natural variation of soil density is not significant over one season. Still, you can manage to be within plus minus 3%. However, for some types of soil, is not true. Depends on the irrigation as well, how much water actually that soil needs. That's why we have right now 2 rounds of calibration. One is after plowing, and one is at the middle of the season. That helps to take care of this problem.
Okay,
Up to some limit, of course.
Yeah, and one more question is like, it depends on what crop is there, yeah? Like for example, it also depends on how deep the roots are going.
True.
And your probe has to, actually has to go that much deep.
Yes.
So do you decide that? Or?
Yes, absolutely. For example, right now we have deployments where in some cases we have vegetables with very shallow root, so 10 centimeter is good enough for them. There are some crops which need around 15 to 20, and there are some crops which go deep to 30. Therefore, root reaches there. So therefore, we have 2 models. One model is single probe, One model is a probe with different, eventually 3 sensors at 3 different depths. But there are pros and cons with each one of them. Right now, what we are doing for the cases which are very important in numbers to be very precise, we actually use 2 separate probes, and then one is at the surface, one goes deeper. In the other cases, 1 probe with 3 different. Yes, they are absolutely required.
Yeah, thank you, madam. Thank you.
Any question? Thank you, ma'am. It's indeed a great experience for all of us to hear your research today. Now, further, I request Dr. R.N. Fursule to kindly come forward and felicitate Dr. MARYAM SHOJAEL ma'am with a memento. Ma'am, please. Thank you, ma'am. Thank you, sir. With this, I declare the closure of keynote session, and we are going to meet for the next keynote session, which is as 3:45 p.m. by Mr. Prasad Shetty, sir. He is Vice President at Capgemini Engineering, India. Thank you all for your patience listening. Thank you once again. Thank you, ma'am.